All right. Well, good morning, folks. Let's go ahead and let's get started. I want to go ahead and try to get done with this chapter today. Yeah, I forgot. I'm sorry. We don't have school on Monday. Monday is, I guess, the Memorial Day holidays, so we won't be meeting on Monday. So what we'll do is we will wrap things up on Tuesday of next week, and then it looks like right now we'll be taking the exam Thursday, maybe Friday of next week. Okay, so I'll let you know. Depending on when we take the exam, we'll either review on Wednesday of next week or Thursday of next week. So what we'll do is we'll take the exam for chapter 12 here next week for sure, either Thursday or Friday. We'll meet, we'll review, and then we'll take the exam, and then we're going to finish up the semester by going over chapter 13 and 14. I'm gonna see how far we can get with the chapter 13 material. I'm obviously gonna try to condense things down a little bit in order for us to fit both chapters in before the end of the year. But what we'll do then is you will not have a final exam. Your last exam will be just an exam on the new material, the chapter 13, 14 material, and then we'll be done with the semester. Okay. So that's what we're going to be doing moving forward. And so let's go ahead and let's finish up with these with the stoichiometry here in chapter 12. And so we left off with this problem yesterday. We worked out this problem yesterday, and we were able to get this done. But what they asked you in this problem is that they asked you, based on the information given to you here, on the balance equation for the reaction, on the amounts of the reactants that you have. First of all, which one of those would be the limiting reagent? And remember, the limiting reagent is the reactant that runs out first. And the reactant that runs out first isn't always necessarily going to be the one that is present in the smallest amount, the least amount at the beginning. It could be, but it may not be. It just depends on the reaction itself, depends on the amounts indicated and depicted in the reaction itself. And so we have to actually calculate. We calculate for the limiting reagent by doing a very simple limiting reagent calculation. Okay, so we'll do a couple practice problems today in order to get that done. But then once you had the limiting reagent, once we know what that is, and remember, the limiting reagent is the reactant that runs out first, and when that runs out, no more product will be formed, and so therefore it determines then how much product will form. So if we wanted to answer part B, which is how many moles of water is produced, and water in this reaction is a product. So we want to find out how much water is produced. We have to figure out which one of those reactants, CH2, C2H4 or O2, runs out first. And we did that calculation yesterday, so please make sure you take a look at that. And come on by after school day if you have any questions and get that done, okay? All right, but what I would like to start today with then is a couple of review problems that I want us to do in order to help us kind of situate ourselves today, and then also for us to move forward. Your homework for this weekend is going to be what we'll be talking about hopefully in just a moment, which is actual yield and theoretical yield and percent yield. And so try to get that done. And then it'll be due Tuesday night. But this problem here, this is from, so that tonight's homework, this weekend's homework is going to be set D. But this problem here, this problem is from set B. I want to start out with this problem though, because it gives us a chance to review what we've done in terms of stoichiometry, in terms of the conversions here. And so let's go ahead, let's start out. So if you need to, pause the video, go get your book, go get your homework. If hopefully you've done this problem already. But if you did the homework, but you weren't quite able to do this problem, then make sure you write it down now. But I want to work out this problem with you and help you out with this. Okay, so go get your book. And if you've done it already, go get your homework. And let's either compare answers or you write down the work itself here, okay, if you didn't get it done the first time. Okay, so let's go ahead then. Let's get started on number 16 from your book. And this is on page 364. Let's go ahead and get started on that, and then take about 5-ish minutes. If you haven't done it yet, try your best with it, and then we'll go over it together. Okay. All right. All right. So let's go ahead then, and let's get started with this. With stoichiometry, hopefully you've read this problem. Okay, so page 364, number 16, it describes a reaction for us that involves nitrogen dioxide, water, okay, forming nitric acid, and nitrogen monoxide. Okay, so first thing you want to do whenever you get these problems and you're doing this, okay, is go ahead and write out the equation. Okay, so hopefully you got the equation that describes this reaction, which is NO2 as a gas plus H2O in the liquid form. All of that to produce then HNO3, which is nitric acid, in the aqueous state, okay, and nitrogen monoxide in the gaseous state. Okay, so that's the skeleton equation here. Balancing it out, then you would have 3, 1, 2, 1. Okay, so that should balance everything out. And so once you have the balance equation, what I remember what I was telling you, if you need to, I would like you to go ahead and write down what you were given in this particular problem. So you always want to go ahead and do that to help you. Okay, so we are told then that to start out with then that we have 5.00 times 10 to the 22nd molecules of nitrogen monoxide. Okay. So we are given this amount here. Okay, so we are told then that we produce 5.00 times 10 to the 22nd molecules. That means the number of particles. So they tell us the number of particles of nitrogen monoxide that is produced. Okay. Okay. So if that's the case, then that's what they give us. What they're asking us to solve for then is the grams of nitrogen dioxide. So the conversion here, folks, is that they give you the amount of one of the products in molecules now, and they want you to convert that and find out then how many grams of nitrogen dioxide to start out with. So this is what you're solving for. This is what you are given, and so we just need the conversion factors to get there. Okay, so that's our conversion. So let's go ahead and let's write that out. Okay, let's go ahead and write it out. Okay, so our starting amount, and so even though the amount, what nitrogen monoxide is a product, what they're asking you is the conversion here is the conversion that will give you the answer to the question, how much did we start out with? How much NO2 did we start out with to produce the given amount of NO right here? And so the conversion still is the same. So this is what we start out with. So yes, it is a product, and this is what confuses folks. Yes, this is a product, but this is the given amount. They give us this amount, and they're asking us to solve for, and this is what we want to end up with, the mass in grams, the mass of NO2. So we were given 5.00 times 10 to the 22nd molecules of NO, and we are solving for grams of NO2. So that's our conversion, folks. And so now we have to figure out what the conversion factors are in order to get that done. And if this is stoichiometry, we're going to use 3 conversion factors. The first conversion factor we have to use has to have molecules or indication of the particles in it. Okay? And we know what that is. That's Avogadro's number. So we're going to go ahead, and it's going to be 1 mole of NO for Avogadro's number, which is 6.02 times 10 to the 23rd. And it's going to abbreviate here NO, which is molecules of nitrogen monoxide. Okay? Why do we use this? Because this gives us, and maybe I'll just write that in here with the caret. So this is molecules, okay, of NO. That's by definition what we learned back in chapter 10. We define the mole as being this many particles, this many number of whatever particles we're referring to. And so we're referring to particles of NO here, molecules of NO. And so we will use this here in order to eliminate that unit right there. Okay. And now we have moles of NO. We want to get to grams of NO2. So we're not quite there yet. So we need the mole ratio now. Okay. So this time we're going to use the mole ratio between NO and NO2. And that's why writing it out here is going to help you. Okay. And so therefore then, if we're going to convert to NO2, this will be on top, NO2 will be on top, and 1 mole of NO on the bottom. Why? Because that allows us to cancel out that unit, okay? All right, so we're almost there. So now we have moles of NO2. We need to get to grams of NO2. We're going to use the molar mass of nitrogen dioxide here, which is going to be 46 grams of NO2 over 1 mole of NO2, and that allows us to cancel that out there. So this then, folks, is a pretty straightforward, pretty simple stoichiometric calculation. This time, so remember, we did stoichiometric conversions for grams, so we convert grams to grams of the components of a reaction. We did that for volume, we did that for moles. Here, folks, is a molecules to grams conversion. And when we went over the stoichiometry, I pointed out to you that we can do any type of conversions here as long as we know the conversion factors, we can do the conversion. For example, they could have asked us, given the number of molecules of NO here, to solve then for the volume in liters of NO2. And how would we do that? Well, folks, NO2 is a gas, NO is a gas, and if the problem had specified that the reaction is run at STP, we would use then at this position here, the molar volume, okay? And so we can, as long as we can remember or we can identify the conversion factors that we need, we can do any of these conversions, okay? All right, so hopefully you set it up correctly there. If not, then make sure you write that down. And so we end up, if you plug the numbers in correctly, with an answer of 11.5 grams of NO2. So what is this? What did this conversion tell us? This conversion tells us then that if we had started out with 11.5 grams of NO2, we would then produce this many molecules of NO. My hope is then that based on this, you can solve for the mass or the volume equivalent to this many particles of NO. Okay? So if you're interested in doing that, come on by and see me, folks, and we'll work that out. But we do have to continue on. So let's go ahead then, and I'm going to save this here. I would like us to work out one more problem. Okay, let's do from your book, and this is from set C, which was Tuesday's homework. Okay, do number 28 on page 371. Okay, 28 on page 371, and then we'll go over it at that point. Okay. Uh-oh. Okay. All right, let's go ahead and let's take a look at page 378. I'm sorry, page 371, number 28. But let me check something really quickly here, okay? And just to make sure that, okay, let's go ahead and let's work this one out, okay? Okay. So we have then, let's go ahead and let's start out. We want to always start out with the balance equation, okay? And this equation hopefully should look familiar to you. We did a similar problem earlier, yesterday, okay? So the balance equation here then is going to be C2. It's going to represent the equation, the reaction between C2H2, which is acetylene, O2 gas to produce for us CO2 gas and water vapor. Okay. All right. The balance equation here is going to be 2, 5, 4, 2. Okay. All right. So that's what we have. Okay. And then now let's go ahead and write down what we're given. Let's go ahead and write down what we're given. We were told then that we start out with 2.40 moles of C2 acetylene and 7.40 moles of oxygen. Okay. All right. So what they ask us in this problem, first and foremost, and let me go ahead and let me make sure they tell us then how many grams of water can be produced. Okay. So they're asking us about the mass of water, the grams of water that can be produced. Okay. All right. So this is a limiting reagent calculation. This is a limiting reagent question, meaning then that you have to determine the limiting reagent first. Okay. And then afterwards, you can predict the product. And so this is a two-step, this problem involves two different calculations, okay? And so how do we know that we have to do the limiting reagent? Because folks, look, what they do is, and I pointed this out to you yesterday, and make sure you remember this, if you were given the amount of both reactants, here they give you the amount in moles, but they give you the amounts of both reactants. If they do that, you have to solve for the limiting reagent. The only time that you don't have to solve for the limiting reagent is when they either tell you what it is or they tell you what the excess reagent is. And if they give you the excess reagent, just folks, by process of elimination, if the reaction only involves two reactants, then you know then that the other reactant is going to be your limiting reagent. Okay? But here they don't tell you that. They just tell you the amounts. They give you the amounts of both reactants. I'm sorry, let me go ahead and write this a little bit more neatly. Okay? So they give us, okay, Those are the given amounts right there. Okay. All right. So the very first calculation we're going to do is a limiting reagent calculus. That is, we have to figure out which one of those two reactants run out first. Okay. And so with that said, then pick one. And I'm just going to arbitrarily pick the first one. Okay. So we're going to start out. We're going to pick this, the amount here for C2H2, and we're going to solve for the amount of O2 that we will need. Okay, so this is the calculated amount of O2. Okay, and so this is a mole to mole conversion, folks. We only need one conversion factor, which is going to be the mole ratio, and so we'll plug it in as 5 moles of O2 over 2 moles of C2H2. Okay, so 5 over 2. We plug that in, and we'll get our answer here as 6 moles. Okay, now again, remember, folks, this is our calculated value. Okay, so this is the calculated value, which means then this is the amount of oxygen needed, not to produce water, but the amount needed to use up, to consume all 2.40 moles of C2H2. Okay, so the question then is, are we given enough? Okay, so let's go ahead then. Remember, we're going to compare our calculated value. So let's go ahead and compare our calculated value to the given value. Okay, so the calculated value is here, which is 6 moles of O2. Okay, the given value is 7.40 moles of O2. And so the question then is, if this is how much we need, are we given at least that much? And the answer is yes, because we were given actually more than what we need. So what does that tell us about the oxygen? It tells us that oxygen is the excess reagent. And if oxygen is the excess reagent, folks, there's only one other reactant in this problem, in this equation, and it's this one here. If that is the case, then this must be your limiting reagent. This is what we need to know. We need to know that this is our limiting reagent in order to go on to the second equation, and it's that second calculation that will answer the question here. And the question then is, how much water will be produced? And so we are starting out then, our second conversion, then we know what we're going to start out with now. We're going to start out with this amount here, 2.40 moles of C2H2. And this time, what we're going to solve for is the grams of water. Okay, so we need to do the first one in order to figure out which one of these values we will use to start with in the second calculation. So you got to make sure you keep that in mind. Okay, all right, so with that said, then now that we've identified what we're starting with and what we're going to solve for in the second calculation, let's plug in our conversion factor. Okay, so this is already in units of moles, so we'll need the mole ratio between acetylene and water, which is a 2 to 2. Let's go ahead and plug that in. 2 moles of water, 2 moles of C2H2, and then finally we need to get to the grams of H2O, so therefore we're going to use the molar mass of water, which is going to be 18 grams of H2O over 1 mole of H2O. Okay, very good. And so with that said, then you plug it in, you're going to get your final answer. Then here is 43.2 grams of H2O. Okay. All right, folks. So make sure you write that down and get the homework done. Okay. So try to get the homework done correctly now. If you can, go back and look over your problems and review them. Okay. Let's go ahead then and let's continue on. So with that said, if you have any questions, come by and see me, folks, and let's and then get your questions answered. Okay? But we got to continue on, and we're going to finish up today by talking about what's called percent yield. Okay? Percent yield, as the name implies, is a percentage. Okay, and the yield part then is the how much product we have obtained. Okay, compared to, since percentages are ratios, we're comparing the amount of product that we obtain to the amount of product that we expected to get. Okay, so it's the ratio between the actual yield, and that's when you run a reaction, you measure out how much product you get. That's the actual amount that you obtain, and we're going to compare that amount, that amount, which we call the actual yield, to the theoretical yield, which is the amount that we expected to get. And the amount we expect to get and the amount that we actually get will never be the same. Okay, which means then the percent yield will never be 100%. Okay, so and I want to make sure you keep that. I want to point this out to you. We never expect 100% yield in real life. In the laboratory, that will never happen. Which means then the actual yield, okay, which is what we get, so the actual will never be equal to the theoretical. The theoretical now, folks, theoretical is the expected amount. This is how much we calculated for. And what this is, folks, we will talk about in just a moment. But those two will never be equal. And since those two will never be equal, the percentage will never be the same. So the percent yield then, folks, and then let me rewrite this up here for you. The percent yield is just simply then the actual yield, which is the amount that we actually get. That is the real amount, okay, over the theoretical yield, which is the amount that we expect to get times 100. So a percentage, basically, folks, remember, it's just the ratio out of 100. So here the ratio is comparing the amount that we actually obtained to the amount that we expected to obtain. And like I said, since those two numbers will never be equal, you will never get to 100%. Well, will you get less than 100%? Almost all the time. Will you ever get more than 100%? Occasionally you will. And for those of you who are moving on to AP chemistry or higher chemistry, you're going to see then that every once in a while you're going to get a percentage yield that is greater than 100%, and we have to figure that out. Okay, so we have to determine why that is the case. Okay. All right. So with that said, then I'm all out of time here. So what I would like us to do then is on Tuesday, then we'll wrap up with this chapter here. I want to talk about theoretical yield. Tonight's homework, set D. Don't worry about that for right now. I'm going to go ahead and reset that for Wednesday night, and you'll do it then. But if you want to take a look at it, the calculation for percent yield is not that difficult at all. It's essentially a limiting reagent calculation if you need it, calculating for the amount of product, which is what we call the theoretical yield here, and then identifying what the actual product is, plugging those numbers in, divide it, and then multiplying by 100. Okay, give it a try if you can. If not, then that's okay. We'll continue with this discussion on Tuesday. All right, have a good long weekend, folks. Happy Memorial Day, and then I will see you on